and even I sent the email with the wrong title, and
it was my fault.
But
I apologize.
Just meant it would be more interesting. Okay. So maybe Aloy will talk about mergers of neutron stars. So it's talk or discussion?
It can be whatever you want. It can be talk, but if at any moment you want to interrupt, just to do it. And well, this is work that I have been doing in collaboration mostly with Martin Overgaulinger, which was a student at MPA, now a postdoc there, under the supervision of Eval Müller and myself. And well, let me see if this works. This works or not? Maybe it doesn't want to start. Okay. So just let me first of all set the stage of what I'm going to talk about. As most of you know, the merger of two neutron stars is considered the most promising site for the generation of the so-called short gamma reverse, which is a subclass of gamma reverse mainly characterized by its hardness and by short duration below 2 seconds. After an initial phase of spiraling due to the loss of gravitational angular momentum due to the loss of gravitational waves in the system, these neutron stars come sufficiently close, and in a dynamical time of a few milliseconds or so, they touch and start to merge. They are mutually distorted by the action of the tidal forces, and the final system that forms is a central compact object, which can be a hypermassive metastable neutron star, which finally end up as a black hole, or directly you might form a black hole, depending on the parameters of the system, depending on the masses and the angular momenta of these objects, and so on. Now, the thing is that...
Do you find it plausible that the neutron star survives for longer time?
Well, these hypermassive neutron stars may survive for a few milliseconds, but eventually they accrete mass and become and collapse. There are some situations that have been worked by mostly by Shibata, where they can survive sufficiently long time, but you know, not beyond a few milliseconds.
Okay.
Of course, if the neutron stars were very, so they could eject a lot of mass away, then maybe they can survive for longer, right? Now, due to the orbital motion and the rotation of the neutron stars, this is just a, sorry.
Just continuation of Demetrius, doesn't this give some restriction on them as sources of short gamma reverse? Because even for short gamma reverse, the duration is normally more than a few milliseconds. It's more like, you know.
Right, but this is just for the what I was telling Demetrius was the duration of the life of this hypermassive neutron star, not the duration of the system, which is set by either the viscous accretion timescale of the torus that forms. You know, you merge and then you form a central compact object. Since you have a lot of angular momentum or sufficient angular momentum in the system, you form an accretion disk, and then the idea is that you either fuel the outflow by some hydromagnetic or thermal energy deposition, or you just extract the energy directly from the angular momentum of the black hole, right? So in the later case, the duration is just set by the spin down of the black hole, so which can be rather.
Exactly, you need a disk for that, right? You need a disk to extract.
Well, for the Blanford-Nagios mechanism, probably not.
You still need a disk.
You still need a disk. Well, but not as massive as in the case of where you release energy thermally, right? Because in that case, you need that the mass of the disk be of the order of a few tenths of a solar mass.
Is that really true? Because you need a field that's strong enough, and then for the field to be 10 to the 15 Gauss or whatever.
Well, if you invoke, but this is if you invoke magnetic generation. If neutrinos play the role, these systems are extremely hyper-accreting. They can accrete masses at rates of the order of 1 solar mass per second. You know, I don't say that all short gamma reverse can be explained like that, right? But certainly these systems will build a signature in the form of a relativistic flow that eventually can produce a gamma ray burst. Right? Probably, well, you know, I have some ideas about how to make a longer duration GRV out of a short duration event. You know, you have initially a deposition into a fireball, and when you release less energy, this fireball starts to stretch radially, and since it's a fluid, it rarefies towards the back. So while this effect, it doesn't make any substantial lengthening of the duration for long gamma ray burst, in short gamma ray burst may multiply the duration by 2 or 3 or 4, as we demonstrated in a paper in 2005. It is simply just that the radial stretching before you reach asymptotic values of the Lorentz factor.
You just mean there's slower stuff piling up later?
Yes, there is stuff which trails, and it's still quite relativistic, right, and hot. So it can well produce a tail in the gamma ray burst, or just help to produce late activity. Not at the scales of hundreds or thousands of seconds. I'm thinking on the prompt gamma ray burst phase. Right?
You still need something to produce the afterglow, I guess.
Well, here you have this fireball, and you have in those mergers. Well, here I put a cut in the equatorial plane, and this is just showing the magnetic field strength. Sorry, I didn't say that. But in those mergers, when the neutron stars come close to each other, there is a dynamical phase where the excess, there are parts of the system with an excess of angular momentum which are just expelled away, and they form a sort of halo around the merger. The amount of mass that you put in that halo depends a lot on the orbital angular momentum of the neutron stars and the mass ratio. Right? For large mass ratios of the neutron stars, what you find is that this halo or this extended disk can be rather massive, a few 0.2, 0.3 solar masses. So this is extended to distances maybe of a few hundreds or thousands of kilometers, and that mass you push away. You know, if you have a halo, you form initially the black hole with a thick accretion disk, but surrounding it you have sort of halo with up to scales of a few hundreds or even almost 1,000 kilometers. And then you are releasing, imagine that you release energy thermally here because of neutrino energy deposition, then you have to push all this mass away. And that's what, you know, here you can have easily in a cone of up to 20 or 30 degrees, you can have a few 10 to minus 5 or 10 to minus 6 solar masses.
This halo, what's the origin of the halo?
You have matter where you know, in the borders of the two neutron stars, which have sufficient angular momentum because of the spin or because of the angular motion, and they can be, just because of tidal forces, just expelled away, right? And you form, if you see the merger, I don't have a merger moving here, but you see clearly that these things happen. Just the outer parts of the neutron stars can be expelled away.
What's
You
the
know,
In the equatorial plane? Or
not only in the equatorial plane, it preferentially in the equatorial plane, right? Most of the mass is there, but not only there, right? You know, in all these simulations, neutrino physics is not extremely well included, and the thing is that if you include this neutrino physics, when you release energy, when you hit because of neutrino-neutrino annihilation, the outer layers of the disk, you will stimulate a baryon-rich wind, a neutrino-driven wind, which will basically fill the whole space, but of course the highest density would be towards the...
But Miguel, what's the density in the halo compared to the density in the...
This is something that it's, you know, I don't know in nature what will be the answer, right? In simulations, there can be a factor of 10 to the 7, the density contrast between the thicker disk and the halo.
But that's just by hand, right? That's the floor that they put in the density.
No. I mean, in merger simulations, you start up with some even a smaller floor for the density, right outside of the neutron stars, and then in the halo you build up densities up to this. Well, to be fair, it's 10 to the 7 compared to the core of the disk, which is about 10 to the 13 grams per cc, right? But this immediately, I mean, this falls down very quickly.
So it's very dilute.
It is. It is, but if you make up the numbers in a cone like this, of 30 degrees, you may have, as I said, about 10 to minus 6 solar masses or so. That's okay. I mean, you put 10 to the 50 ergs there, and you can speed up this thing to very large Lorentz factors. Actually, we argued in 2005 that this is the reason why short gamma ray bars may have a larger Lorentz factor than long ones. Simply because you put...
So you're saying that you're actually only accelerating matter in the halo, not matter from...
As you release, well, this is the initial configuration. So now, if you have an extended the energy release, because of course neutrinos and antineutrinos can also annihilate over here and so on, right? You may extract with time also mass from the disk, which will flow into the main outflow, right? This is not only the mass that you have here initially, but also the one that you add up in the course of the evolution. Right?
So neutrino physics is included in simulation?
In which simulations?
Well, you just described all
well, yes. Well, you know, at the level at which this is done, the best is by Raffer and Janka. They just do a post-processing thing where they see which are the thermodynamical conditions in the merger. And then they estimate which is the energy released by neutrinos and antineutrinos. You know, you cannot couple the whole thing so far very well because it's not a spherical symmetric configuration. So what works in supernovae, this ray by ray Boltzmann integration, it's obviously not right in this system. So the best you can guess is to do a post-processing analysis of the energy release, right? Indeed, we have worked out what is the what is the energy released due to neutrinos, including all ray tracing and general relativistic effects and so on, but assuming a static background. So assuming that you have like a succession of quasi-equilibrium states, right, and then you just estimate which can be the energy release in such circumstances, right?
Yeah, but it's
And what's the elimination mechanism for the other four?
Okay, so here
Is any collimation?
yes, there is collimation. The outflows can be collimated with angles from 15 to 25 degrees, right, or 30 degrees or so, and simply set by the walls of the torus. Basically, the initial angle that the walls of the torus form with the rotation axis of the system tell you which is the collimation of the flow. So if you have a very thin disk, you expect very little collimation. But these systems are rather, hyperacritic, so they heat up a lot, and if you have viscosity there, the disk puffs up in the vertical direction. So you have.
So it doesn't cool efficiently.
The disk cools initially not, because the accretion is very high, right? It doesn't cool efficiently, so it puffs up. Yes, but still. You know, you are emitting here a flux of the order of a few times 10 to the 53 ergs per second in neutrinos. So most of it just is catched up here, right? But if just 1% or so, it just goes away and releases energy here, it's already quite some achievement.
And what's the scale of the acceleration?
The scale of the acceleration, what do you exactly, how fast is this, or at which distance you reach which Lorentz
It has
factor?
to become supersonic, the outflow, in order to
Oh,
keep
very
keep
quickly. I mean,
simulation
a few Schur radii away, you become supersonic, and actually, at scales of 100 kilometers or less, your Lorentz factor is of the order of 10.
it's basically the Blandford race sort of solution, right? More or less.
Yes.
Would you predict precursors in this scenario?
Precursors. Well, let me see. I have to think about it. It depends on how is the structure of the halo, right? If you have a halo which is very inhomogeneous, perhaps you may have something like that, but I don't think
So
so.
the halo exists before the...
Yes, this is standard thing that forms during the merging phase.
and And another question, since this is so close to the black hole, I would also expect to be blowing into the hole.
Right. If I could have another talk here, I could just show you. Well, I think I have. So maybe I don't know. Should I change? Just to show you.
It's not going anywhere.
This was about other thing, but never mind. So let me see. Where is it? I think there should be something.
You're the first one to give two talks.
Two talks? No, it's because in these talks. Let me see. This is just to show. Okay. So. Sorry for this detour, but okay. So those are this is some work that I did with Rainer Virkel about. You have here the system with the disk, which is those are the antineutrino sphere and the neutrino sphere, right?
Well,
the disk.
what are we seeing?
Sorry.
What are we seeing?
We are looking at the amount of energy released. This is the zeros component of the for vector energy deposition, right? So the energy deposition because of neutrino-antineutrino annihilation. In this work, what we did is to work out the trajectories, the geodesics, the known geodesics that neutrinos follow in the background provided by the black hole, right? And then the thing is the following: this line over here, right, sets the boundary between regions where you release, neutrinos and neutrinos do not only release, when they annihilate each other, do not only release energy, but if they encounter over here, right, they will have a net momentum perhaps like this, right, in the system. So wherever the radial component of the four momentum energy deposition it's positive, this means that this energy could eventually escape to infinity and reach the observer, right? But if it's zero or negative, this energy will fall into the black hole. So the location of this boundary is parameter dependent, depends on the mass of the black hole or the ratio of masses of the black hole to the mass of the accretion torus. Depends on the spin of the black hole, because if you have a self-gravitating system and you increase the spin of the black hole, the disk will concentrate more towards the equator, and then although you would have a larger total amount of energy released, the point is that most of this energy will also, or a fair fraction of this energy will go also to the black hole because it's released in regions very close to there. So this is a scale, this is a log scale, I don't have here the scale, but here, I mean, you have, here you have some indication. This is just in units of hertz per cubic centimeter and second, something like that. So you see here it's how this goes. So in this part over here, you have an order of magnitude much more energy than over there.
So the dash lines are
Yes, the separation between regions where you put inflow and outflow.
Miguel,
Yes.
maybe a stupid question. What's the relative, say, luminosity or energy released by neutrinos versus other sources of energy like viscosity?
Oh, you are asking the million-dollar question. What we have, I can tell because it depends on the interplay, which is the magnetic field strength and topology, right? Which is the exact value of the spin of the angular momentum and its mass. You know, the Blauvstein mechanism scales with a square, m square, and so on and so forth. And here you have what we have tried to show here is how, for example, the efficiency, so the of the process scales with, for example, the mass of the torus, right? And the dimensionless angular momentum of the black hole, right?
What is the m dot here?
What is what?
The mass loss, the accretion rate.
Oh, in this case, what we are taking just a hydrodynamic torus which is in equilibrium, right? It's an equilibrium configuration, but for these conditions, we would expect something like 0.1 to 1 solar masses per second. It's very
At some point, the neutrinos become trapped. So
right. So this marks the antineutrino sphere where antineutrinos are trapped, and this is the neutrino sphere where neutrinos are trapped. So this is all considered. So we have trapping, and we have semi-transparent regime and free streaming.
And it's a solar mass black hole, so
Yes.
structure radius is about a kilometer.
3 kilometers, yes, something like
So
this.
it's
It's about 3 solar masses black hole here.
It's 3 kilometers. And it's quite far away from the disk is quite far away.
No, it's not the disk. This is the neutrino sphere and anti-neutrino sphere. So the actual density distribution would extend to much closer. So this is just to show where you are releasing energy. Actually, this would look like, if this is the density distribution, this could look like this and this, right?
It's interesting to notice how quickly the annihilation rate falls off. So you go from 21 to 29.
Great.
Factor of
That's
4.
actually very interesting. And,
So that line is really important because
It's-
most of the
yes, yes, I think so. I think also so. And also, actually, I think it matters whether this, it's not only a thing. I know that it matters whether these lines of equal energy deposition rate per unit of volume are either plane parallel, so perpendicular to the axis, or they are more radial. Because depending on that, you may form outflows with very different properties and topology, right? Actually, it's easier to accelerate the flow if these lines are plane parallel to so perpendicular to the rotation axis of the system.
So I can't read that. That's 31, right? Or is it 20? On the line, on the dotted line. Dash
Here
line.
is yes, 30.5, 31 or something.
And on the dash line?
Yes, it should be 30.
Okay. 31. Okay, so it's 2 orders of magnitude and a factor of 4 over the.
But what is more interesting is this dependence of well, okay, I plot here 2 lines. One thing is that for the total energy, the efficiency of the process in total, including these 2 regions, right? Or only the efficiency of the process by looking at the up region, which is presumably the energy that can see a distant observer.
How do you define the efficiency?
The efficiency is defined as the energy deposition rate, so the luminosity of the neutrino process divided by the sum of the luminosities of neutrinos plus antineutrinos. Which is, here since we are doing idealized models, it doesn't make, it's not, I would say it's not appropriate to give the absolute values or the absolute scale. It's better to talk about efficiency, so relative to the amount of neutrinos and antineutrinos that you produce in the disk.
So it's a few percent, that's it.
Yeah, so the good, yeah, it's a few percent.
few percent is a lot. I mean.
Yeah. I know. So this is a few percent for what the observer can see, which is basically this red line. But the good thing is that, well, okay, this was a preliminary figure at that time. We have many more points now, and we can really follow this. Is that it has a maximum.
Well, I didn't get the answer to my question before about the
efficiency.
Yeah, the energy released in neutrinos versus energy released in other processes like viscosity.
You mean the total? What's the question?
No, but
Everything
the other
goes to
process is
neutrinos,
just
no?
this energy won't go away. I mean, it's just
Something will go into heat.
So you have to release energy. This other energy would be in the form maybe of internal energy or whatever, and this is not going to escape in principle, right? It is.
What the typical spectrum you use?
That's a very good question.
Okay, the typical spectrum here. What we have done is just we just take for the propagation of these neutrinos. They are emitted basically at these surfaces, which have a distribution of temperatures, which go from about 2 or 3 MeVs to about 15 or 20 MeVs.
So you assume thermal or
thermal. We assume that we make the simplification that the neutrinos are emitted from like black body surfaces, which are the neutrino spheres, and then they fly away with this temperature. Yes, I know.
Borodov had some papers on.
Right.
But the efficiency is very sensitive to.
That's right, but we have worked out here many different models with different ratios of neutronization, so YEs and so on and so forth.
Oh,
so we have also explored the geometry, and we have also explored many things to be sure about this efficiency. And you're right. It's not the same to have both surfaces at the same distance, as for example it was considered by Miller and co-workers in 2003, as to have a more physically motivated situation where you have, this is neutron-rich matter, so anti-neutrino sphere should be closer, deeper inside than the neutrino sphere, and these sort of things.
So you explored these parameters basically using just one initial equation of state for each of the neutron stars, or you just vary?
No, here I started the situation assuming that the merger has produced and forms this system, a central black hole plus a torus. And then I parameterized my ignorance. We did many more things, like studying what is the sensitivity of to different possibilities, right? Geometry. Well, what if you form basically a flat disk, and then we explore what happens in this case. What happens if the neutrino sphere and anti-neutrino sphere are all together and they are restricted to a very small region far away from the black hole? What if this is just like in a neutron sort of the neutrino sphere. You have really neutron star, and then the neutrino sphere is spherically symmetric. All these games were played.
You have rotation of the black hole?
Sorry?
You have rotation?
You will have rotation. Yes, we do. Actually, okay.
That's it.
Can you just maybe tell us what you don't have in your model?
Well, okay. So let me see if I have a plot.
Before you go, the first plot is just flat.
Yes, this is just a flat disk,
Thin
thin disk,
disk.
which is the most efficient configuration
Most efficient for energy.
for energy release, but less efficient for flow confinement. So the worst for energy releases are spherical neutrino spheres, and somewhat intermediate are this kind of
And looking
thing.
at this plot, what can I see? What can I see about the collimation? So,
Oh, in this case, very little, but okay. In this case, very little because here you have simply an idealized flat disk with a given angular momentum.
No, but you can see at a given height in Z, the deposition is higher near the axis, so that already gives you some collimation, right?
Right. I mean, and also you can see that there is some. I mean, here this is not extremely fast rotator. What I wanted to show is how it depends. I don't know if I have it here. Let me see. Maybe not. Well, I don't know if I have it. Let me see if I have some in the backup slices of another talk. Let me see if it's over here. This one. Oh, yes.
Presumably get the helmet.
Yes, yes. Yeah. So this is just the influence of the of what? Oh yes, whether the disk are in those idealized cases, whether the disk is subkeplerian, Keplerian, or super-Keplerian. The idea is that if you have a thin disk, so pressure is unimportant. So basically, the disk is Keplerian. But if you have a thick disk with pressure support, then the disk is subkeplerian, highly subkeplerian, and for fun we just try I don't know if we try super-Keplerian disk or something like that. But the point here is that when the disk is subkeplerian, right, you tend to concentrate the energy release. Those are just integrals along radial directions for different angles from theta equals 0 to 90 degrees of the amount of energy released by neutrinos and neutrinos as seen by an infinitely distant observer. So if the disk is subkeplerian, you tend to concentrate most of the energy release around the axis. Right? So when you do the radial sum, this means that you are not releasing everywhere the same, so you have also a natural way of collimating this thing, because you are releasing more towards the axis. But if the disk rotates very fast, or even at Keplerian rates, then what you see is that you release more energy along a cone. So like in a hollow cone, right? It would be something like I don't know if I have to sketch a new draft because this is just a thing to listen. So you have the disk again, and what this tells you is that you preferentially are releasing energy in shapes like this. So these equal surfaces of neutrino annihilation do not look like what I was showing in those other pictures, like more like that.
The Keplerian case, is it still here on the plot?
I would say
There are three plots.
that's
lines.
yes. I don't really recall. I recall that we tried sub-Keplerian, and this was this case, and this is Keplerian, and this is super Keplerian. We did this one for fun, just to see what.
Well, the super Keplerian is also, I mean, you should expect outflows with this because it's really supported. So you should have also, I don't quite see what, but you should have also, you know, baryon-rich winds.
Right,
slow winds,
right,
and-
right. But this won't be in the core of the disk where basically when you have the neutrino sphere. This has to do with the angular momentum at the level of the neutrino sphere, right? Not at the level of the outer disk, right? So this is just to see the evolution. Actually, I don't expect this is a physical realization of the system. It's simply to see the trend, right? We just saw that this is sub-Keplerian, and then it goes like this.
So are you assuming that all the neutrinos are radiated? Because at some point they're trapped and infected into the hole, right? So
In this case, no. This is only this only accounts for unobserved at infinity. So above this separatrix I sketch in the plots. This is for
that's
the
what's lost
energy.
into the hole. But I mean, even in the disk itself, all the neutrinos aren't released. At those accretion rates, they're infected. So you have an infection-dominated flow.
Oh, well, yes, of
Even
course.
for
I mean, this
neutrinos.
assumes a steady state. This is a steady state picture.
So you don't account for that.
Yeah, no, because we are doing this in a steady state. We have, this is the machinery ready to be incorporated in a hydrocode, in a dynamic code. But of course, I mean, each of these simulations lasts as long as the whole hydrocode simulation. So, you know, I mean, it may take, a complete simulation may take 6 or 7 months to finish over 1,000 processors. So it's still a bit too much. So we want to improve a bit on the method to include true neutrino transport here.
What's the problem?
You know that you have a non-local problem. Transport is a non-local problem. So every time you pretend to compute, which is the energy deposition rate, you have to send like a few tens of thousands of rays to estimate the discretize at the discrete level in each of your computational sets, which is the amount of energy released by neutrinos.
But I mean, if you just put already, if you know where is the photosphere and you assume thermal
But you have to
spectrum,
compute it every time, because this evolves dynamically. I mean, it's in a steady state is what we have done here, right? So the thing is that, okay, use the same, but now for the conditions that you have at every moment, estimate where the neutrino spheres are, and do all the ray tracing.
and you do it in curve metric?
Yes, this is in Kerman.
Because this is rotating. So.
Yes.
And this case doesn't really matter because the frame dragging goes like 1/r cube. So
No, but it matters. Actually, as we show here, as I said, the efficiency of the process is very different depending on the A parameter, and it has a maximum, as I showed before.
because the disk is
The thing is that it's very interesting stuff because, okay, as I show here, this is the dependence with the spin of the black hole. So it has a maximum around A.6, and the point is that in self-consistent models where you have a equilibrium tori, the location of the neutrino spheres and of the tori depends on A. So the larger A, the closer the cusp and the center of the disk to the black hole. So if you get too close, then you release most of the energy in this region over here and flows to the black hole. And so there is a trade-off between how close you get, and which depends on A, and the amount of energy released in the up region, what we call the up region.
But this is for a steady. I mean, your disk is going to be convective in reality. These parameters. So I mean, I think it's not that.
And also, how do you estimate that line? Because if you're depositing energy, there's going to be a blow-off into the hole too, right? Because you're increasing the pressure above the hole.
Well,
pushing gas
you mean here? But here, okay, in the cusp of the torus, there is very little amount of mass. I mean, you know, most of the mass of the torus is in the core of the torus. So you mean if I release energy over here, what happens? You just
No, even
push
just
a tiny fraction of the
from
torus.
annihilation. Like, so how do you compute that dashed line? The dashed
Oh,
line
simply I look at the sign. I have a energy release for momentum vector. So the V0 component is the amount of energy per unit of time, and the VR component is the that's being whether it's going in the radial outgoing or radial ingoing direction.
But based on what? Based on the annihilation, or just
Yes, you have the annihilation integrals. I mean, we just generalize to general relativity what it's very well known for classical dynamics.
Right, I'm saying if there's annihilation along the axis, then the
Yes.
pressure is going to go up, and you're also going to push some of the deposited energy into the hole.
But the momentum is in the upward direction. So
There's-
you put
the pressure
also
gradient is
momentum
in-
in this direction.
Right, but the pressure gradient is
Right.
in all directions.
You have to overcome the run pressure. This is known. I mean, we have also worked out together actually in 2000, right?
Yeah, no,
You have
I'm
to
saying-
overcome the run pressure.
I'm
Of
saying
course.
something different. I'm saying that some of the energy that you deposit is going to be pushed into the hole. Or do you account for you don't account for that, I guess.
Actually not, because as I said, you are putting momentum in this direction. If this matter is falling in, then you have to overcome the run pressure. That's absolutely. But once you overcome the run pressure, this pushes away.
Okay.
You have a net pressure gradient.
Okay. I'm not talking about ground pressure. I'm talking about the pressure
No,
that
but you
comes
must have,
from
you must
depositing
have
energy.
momentum conservation.
No, you have a positive. So the pressure goes like this.
But you should have flow through the
Yeah, it's going to push stuff down.
Initially, yes. I mean, initially you have basically a free falling thing along the axis.
No.
Right, but once you you build up sufficient amount of energy there, you stop this free fall, and you build up a negative pressure gradient, which acts as a
But
force.
still, whatever wants to go into the black hole
Yeah.
does. Yeah. There is no strict boundary condition.
No, because as I said, well, that's okay, but we are also releasing momentum in this
You
direction.
have to conserve momentum.
So we are also
I think
releasing
you're just not
momentum.
computing that yet. You're just computing the annihilation.
Well, when we mimic this process in actual simulations, it is what happens.
So nothing goes
You
down.
push, only goes down what is inside of here. One can see a clear.
Those errors, are they velocity errors?
Sorry, I just.
I didn't
Actually, it's a simple way to explain it again.
Tell me. While I'm looking for
Because it's, as you said, it's the ratio of total momentum to total energy. That's what's important.
Right.
So I mean, if you deposit
Right.
enough momentum, if the ratio is is not very small, you must conserve momentum. So
Right.
maybe a small fraction will get in if you ignore gravity. But
Right.
so that's what you have to compute. It's just the total ratio.
outside the
Momentum to energy deposited.
But there's also hydrodynamics because there's shocks laterally.
So
There
you
could
see
be pressure
that's what
gradients
happens.
pointing in as well.
Oh, sorry. Yeah, right.
So it's a pure pair.
we release energy there, and well, actually, maybe this is not too well focused, but basically, you form sort of a separatrix between matter that falls in and matter that falls out.
And that's that line that you plotted.
Yeah. Well, basically, that's in dynamical simulations where we have taken similar deposition maps mimicking what happens in nature somehow. Okay. But this is for the typical neutron star.
There is some flow from the disk.
Right,
Torus,
because
yeah.
we are releasing energy all over up to 45 degrees or so. So the outer parts of the disk just are expelled away.
This is a slow.
A slow baryonic wind. Levinson and Eichler has worked out some collimation mechanism out of this. I mean, you expect that naturally to happen.
Miguel, at Rebel Oboroto found much more efficiency, increase in the efficiency,
Yeah.
kind of the spin
40
of
minutes
the black
into
hole.
the
Sorry?
So at Rebel Oboroto had found that increasing the spin of the black hole, you can get like 2 orders of magnitude increase in the efficiency of neutrino annihilation.
He's thinking, I tell you that the I don't recall right now if he includes true neutrino transport or an approximation, a local approximation to neutrino.
I think these are rather thinner though, because
Right.
they're for more for
Right,
last
so
summer.
he's thinking that if you have efficient accretion, you have to have always a thin disk. So this may change the picture a bit, yes. But we have covered this case with very flat disks, or thin disks, and it's true. I mean, those maximize the energy efficiency of the output. That's absolutely the case. So his argument goes like, if you increase the energy deposition rate, then the disk becomes thin, and eventually, well, you know, it's very efficient in releasing these neutrinos and antineutrinos preferentially along the rotation axis. So I don't see any incompatibility between our modes.
It depends on the spin of the black hole, though. He increased the spin from 0 to close to 1, he found 2 orders of magnitude increase.
I think he has not accounted for the amount of energy that goes into the black hole in the way we did. And actually, there are several works by Miller, by Asano, and also by Salmonson and Wilson, previous works accounting for these effects. So these general relativistic effects, if you count them all properly, can make a 25 to 50% increase in the amount of energy released by neutrinos, efficient energy, right, in the up region.
It's very,
But not a factor of 10. Right. Okay, so maybe I turn back to...
yeah, let's hear about Kelvin Hamilton.
I'm sorry for those. Okay, so I think that I set the stage quite a lot already. So let me see. Oh, well, okay. The point here was that this is the. I have to recall what was the point. Oh, see, yeah. The point here is to show that the magnetic field in the contact layer of these two neutron stars it develops, it amplifies because of the development of Kelvin-Helmholtz instabilities, right? And well, the question is that, let me see, if well, if this happens, of course, if you have an initial seed of the magnetic field, if it's completely unmagnetized, you won't see any effect, right? But the thing is that the exponential amplification of these small seed fields can lead to a very efficient and a strong magnetic field amplification. And then the maximum magnetic field strength that you get there is limited by the nonlinear dynamics of this flow, rather than the linear growth and whatever other saturation mechanism. And here basically it's a competition between the stress on the flow and the work against the fluid forces, which makes that magnetic energy, once you reach a maximum, may decrease or level off. So Price and Rosebach in a science paper in 2006 and in a later paper of Rosebach in 2007 obtained that the amplification of the magnetic field is such that starting from relatively moderate seed fields of 10 to the 13 Gauss, quote, moderate, you may reach values of the magnetic field strength in excess of 10 to the 15 Gauss. Now, the results of these works are much handicapped by the lack of an adequate numerical resolution, particularly in the nonlinear Kelvin-Helmholtz phase. And this is because, and therefore they cannot draw any definite conclusions on the maximum strength of the field or on the back reaction of the flow, of the magnetic field on the flow. Actually, the maximum field was a function of the numerical resolution, which tells you that something was not completely right. The better resolution, the higher was the amplification. So if you continue going on, so infinite resolution yields infinite magnetic field, which doesn't look very physical.
And why is it different from accretion disks?
Well, here is
stable, and here.
Well, you have a contact layer. You have a really, which is with a very fast, relatively fast shear, and presumably also antiparagel magnetic fields. So it's prone to Kelvin-Helmholtz instability. There's no doubt about this. The question here, or what I would like to address, is whether these results of Price and Rosebach are fine, and what really limits the growth of the magnetic field, if anything.
But I guess the point is rotation is important in this case. The whole
rotation is important for the Kelvin-Helmholtz to set the shear so the velocity difference or the relative velocity between the two neutron stars.
Can you draw a picture to show where is the sharing?
If you allow me, okay. I'll do it. I have a sketch.
Yeah.
So imagine that the two neutron stars come close to each other, right? So then one is rotating like this, one is rotating like that, right? In whichever frame you want. I mean, and then you have a density. You may have a density variation or not, but you have certainly a shear in velocity. So here you start to develop all this Kelvin couple that we have seen in the movie, right? This is actually a simulation, right? And you see that in this layer, as the merger proceeds, in a later stage, the two neutron stars form this stuff, and then they.
So they're not synchronized.
Not necessarily. Yes, there is a shear. There has to be a shear. If they are imperfect, so if the velocities matches, then nothing happens. But this is very unlikely that this is going to happen.
Yeah, why? Close by.
No, I mean,
tidally.
Well, but if you have a small velocity difference, you would start to develop this shear interface, right? I mean, even small. I mean, and take into account that the synchronization is okay while they don't touch, but as soon as they start to interact, they will start to slow down each other and produce some contact shear, decompress, and
that's what happens actually.
Right.
I thought that in reality, one of the stars disrupts first and form a disk.
Depends on the mass ratio. If the two neutron stars are equal, why should one be disrupted first and the other later?
Because there is this relativistic instability, so you know it's very sensitive. So
fine. Normally, if one of the stars is more massive than the other, the less massive will be more compact, and the more massive will be disrupted first. But if you have equal mass stars, then more or less they undergo the same evolution. Of course, at some point, one will undergo a slightly different evolution. But in 1 or 2 milliseconds, which is the time scales which we are talking about here, this year happens. This is not only a result obtained by Price and Rothko. Estlin and co-workers have worked it out. The group of Shapiro, the group of Rezzola in Bonn has obtained similar results. So,
Miguel, what about equation of state for neutron matter here? Because
here,
yeah, there was old paper of Blinnikov and Novikov and somebody else. They showed that if you remove a fraction of mass of neutron star with just floats due to just equation of states, how it works here?
okay, they are using a realistic equation of the state, right, for nuclear matter density with some plus some leptonic table for the pressure degeneracy. And the exact equation of the state, I don't know if it's Latimer-Swesty or Sen equation, probably Sen equation of the state what they are using here, right? And some extrapolation at low densities, meaning low, meaning smaller than nuclear matter densities, with 10 to 13 or so people below. So they are accounting for this microphysics principle. What I was saying was that oh yes, so they perform numerical convergence tests and they found no bound on the maximum magnetic field strength. So they could only speculate about which is the saturation mechanism to saturate the growth of the field. And there are basically two possibilities. But this is not a simulation result. It's just assuming two possibilities. Either the magnetic field reaches kinetic equipartition, meaning that it's the magnetic energy is of the same order than the kinetic energy, and then the maximum fields are of the order of 10 to the 16 Gauss. Or, the most unlikely thing, you reach thermal equipartition, where the magnetic energy reaches levels comparable to the internal energy in the system, and then the magnetic field strength can be as large as 10 to the 18. Right. Other groups have addressed a similar problem with different degrees of sophistication in the global numerical simulations. By global, I mean that they include the two neutron stars, the whole dynamics of the flow, and so on. And they have found well, different results regarding the maximum magnetic field strength and and the saturation level. In our opinion, these global numerical simulations had not reached sufficient numerical resolution to study the instabilities that develop in the contact layer of neutron stars and turbulence associated to it. We need what we call local numerical simulations. That is, we focus on a very small patch of this contact layer of a few hundred meters and look at how this Kelvin fold grows, right? Otherwise, you are basically over. In addition to this, SPH techniques, which were used by Price and Rothbach, are known to be much more viscous than grid-based methods. And even for the best resolution using the vertex center mesh refinement in global models, they get a resolution down the surface of the neutron stars of about 350 meters. We are using in our simulations in 2D 10 centimeters or 80 centimeters in 3D to resolve appropriately the development and the saturation of these Kelvin folds. Now, which are the goals of this study? Well, first of all, we want to understand better how the magnetized Kelvin fold instability works, and which are the influence of the numerical systematics, like the resolution, the boundaries, and so on and so forth. Now, we want to also sketch which are the generic profiles of the saturation and of this instability. Assess the results of Price and Rothbach regarding magnetic field strength and the growth times of the Kelvin fold instability, which are the saturation mechanisms, which are the dynamics of supersonic shear flows, because in those cases, in those neutron stars, you can have subsonic or supersonic cases depending on the rotational velocity of these neutron stars. And what we use are dimension. On the one hand, to better understand these dynamics, we use dimensionless or scale-free local numerical simulations, right? And in order to assess the results of Price and Rothbach, we will use what we call merged-oriented local numerical simulations, where the initial conditions are trying to mimic what we expect in this merger. And to do that, what we use is a new magnetohydrodynamics code. It's not relativistic, it's Newtonian, but for the velocities and internal energies that we have in these contact layers, as a first approach could be sufficient, which is designed for the study of instabilities and turbulent systems. So, a few words about the code. It's a flux conservative finite volume Eulerian formulation of the ideal MHD equations. It's based on high resolution shock capturing methods with, for example, various high order reconstruction algorithms from second order to ninth order, right? We use also fourth order Wino schemes or up to ninth order monotonicity preserving schemes. We use also approximate Riemann solvers based on the multi-stage method of Toro and Titarev. Self-gravity is included. We have a Poisson solver in the code. The divergence of the magnetic field is skipped to zero numerically by staggering the field in cell phases using a constraint transport which resembles that of Gardiner and Stone, or the group of Delzana. And this is a key point, because the volume average hydrodynamic quantities and surface average magnetic fields and corner average electric fields are variables with different properties. And you have to interpolate from volume average to point values, or from point values to surface values, and so on. And this has to be done with a lot of care not to lose the high order of accuracy of the code. Otherwise, if you do it straightforward, as has been done so far in many papers, the order of your code is 1 and nothing else, right? And this kills completely your results. For the same resolution, you get basically dissipation.
Have you demonstrated that? Or have
yes, we are preparing a paper on that.
So you can show that codes are first order if they don't use that?
Right. Actually, Delzana already, and Mignone had the suspicion. Well, Delzana had a approximation which is third order accurate, right? Yeah. We show how to do it consistently up to nth order.
So you're hopefully going to show us this? Or
no, not today. This is work in preparation. But okay, this is done, and just to show you how complex it is. if you want to, normally people in 3D does simply the solution of 6 Riemann problems, one per phase. In order to do the consistent high order update of the induction equation in high order, you need to resolve 54 Riemann problems per cell. Right? It's a lot of work.
But sorry, just
it's not all of them are not so complex. Many of them are just simplified Riemann problems. But just to give you a flavor, how complex can it be?
Right. But actually, so you made a big statement. You said that all previous MHD simulations
1D. Those are except Londrillo and Delzana, those are basically first order.
Wow.
Yeah, it's constraint transport. You just do if you just take basically to get the central magnetic field out of the imagining 1D, right? If you just make the VI minus 1/2, VI plus 1/2, you just take the average of these two fields to get the central, you are just first order.
In the conservation of...
In whatever. I mean, you are just doing first order because you are just doing a linear extrapolation of the fields.
And if you do higher than linear, then it's higher?
Right. But this is for this case. But now you have in 2D and 3D, you have to have a proper computation of the electric fields at the corner. And this is very sensitive because it's not sufficient that you say, okay, I have volume average hydrodynamic variables, I estimate the surface average here, and then how do you compute this? From these surface averages, just by summing up these 4 things and averaging. This is first order.
You have many others surfaces.
Well,
so
but you have 1, 2, 3, 4.
Direction and
Typically, well, typically, how do you compute the flux? How do you compute the electric field here? You just take the average, or either an upwind average or an average of over 4 points over 4.
You have values at the cell or interfaces, yeah, and then you interpolate into the corner using whatever
interpolation at which order?
you prefer.
I'm consistent with the Riemann solver and these sort of things. Well, you know, I mean, you have to.
Riemann solvers gave you the electric field.
Right, but they give you basically you compute these electric fields to compute the fluxes, right? And then the question is that you have to be consistent, and there is a feedback, right? Because you have to get later the fluxes of the volume average variables like the momentum, the density, the mass, and so on and so forth. So, as I said, I have only seen in the literature to compute the electric fields here an averaging over 4 points. That's it. Or I take, as Gardiner and Stone do, they look at the upwind part of the wave and these sort of things.
Yeah, but if you do, well, as I say, not linear interpolation, but just high order interpolation, you would expect
okay, but if you do high order,
second on the scheme.
Okay, but if you do high order interpolation, you have to take into account that this high order interpolation in the magnetic field has to be divergence free and these sort of things. I mean, you have to couple perpendicular directions, and what I say is that normally,
The initial configuration of the magnetic field is something you put by hand?
Yes.
Oh, well, maybe last question about it. That's on a uniform grid, huh?
We have worked out, well, the code can work uniform in a linear coordinate space.
Make sure that all it's highest and first order.
Yes, you have to take into account.
It's difficult if it's not uniform grid.
Right, that's what why you have to take into account. It comes when you work with volume average quantities, surface average quantities, and point-wise variables. When you take that into account in the interpolation of the variables, then it is all included. So that's why it's so complicated.
So you're saying it doesn't matter whether it's uniform, not uniform. So the algorithm is general.
Okay, the algorithm is general. Right. I mean, if you formulate it in general curvilinear coordinates. Fine. So sufficient for the code. Now, for the magnetized Kelvin-Helmholtz instability, as all of you know, if you have this Kelvin-Helmholtz, the Kelvin-Helmholtz instability leads to the exponential growth of perturbations, even in a non-magnetized shear layer. You have just the relative velocity between two fluids, right? Now, if a plain Faragel surface layer extends over a thickness D instead of being in a vortex sheet, so just a cut. It just is smooth because physically you may have a smooth transition. Then all modes with wavelengths larger than this width are unstable. Modes with wavelengths smaller than this width are stabilized by the shearing between the two fluids. Now, it's known that after a phase of exponential growth, a stable Kelvin-Helmholtz vortex forms. And what we will assume in the following is that we have, the notation will be that U0 is the velocity difference across the relative velocity between the two layers. Ca is the Alphen velocity, A is the Alphen number, and B is just the magnetic field strength, which is assumed to be parallel or anti-parallel to the shear layer. So it goes like this, or it comes like that. Why is that? Well, because if you have a magnetic field which is perpendicular to the shear layer, when you shear it, it will be transformed after a short period of time in a parallel magnetic field. And if the field were simply orthogonal to the surface, what it would do is just to add up to the magnetic pressure. So the magnetic pressure would add up to the thermal pressure and would modify very slightly the dynamics. It is known from the linear analysis of these systems that if the Alphen number sorry, this should be the other way around. If it's smaller than 2, then the flow, the shear layer is stable, and there is no growth of the Kelvin-Helmholtz instability. If the Alphen number is otherwise larger than 2, so weaker fields, the instability develops similarly to the non-magnetized case, but its growth and the nonlinear saturated state depends strongly on the magnetic field. There are a number of practitioners in this field. I don't know if I have been sufficiently exhaustive here. If you know anyone else.
Is there any simple physical reasoning that explains this?
Oh yes, you have a parallel magnetic field. You try to move across the magnetic field. You try to make these eddies, and you can't, because magnetic tension stabilizes the flow.
Yeah, I have a question. What's the difference between this setup and Shearbox doing MRI simulations?
A shearing box doing MRI simulations.
Why don't you get MRI here?
There you have a gradient. You don't have simply two states. You have a gradient because you want to have a gradient in rotational velocity or a gradient in entropy or whatever to develop MRI instabilities. So here it's just, you can, actually we have a paper on that, and these Kelvin-Helmholtz modes are just, and you can consider them as a limiting case of MRI, where the gradient is just a step function. Right?
Yeah, okay, so it's sort of the definition of magnetic Kelvin.
Right. It depends, it's a matter of taste. You can say that Kelvin-Helmholtz modes will be those which will have, the limits will be simply the limiting case. If you would have just a stratification of the medium in velocity.
But even if, the MRI just requires shear of the magnetic field, even if you don't have,
you don't have rotation.
Here? No, here not. I mean, what is...
Shear box. That's what they do in simulation.
Then it's a different problem.
Right.
Why is it a different problem?
Because shearing box without rotation is just a linear shear flow, and that corresponds to a really marginally critical case.
Right.
So Q equals 0, or if the omega, constant angular momentum. So that's not a Keplerian disk.
Yeah, but I mean...
And so then the MRI just shuts off, and Kelvin-Helmholtz and radial instability turns on.
Right, you're thinking on disks.
Yes.
But MRI has been also worked out in stars, and for that, what you need is either an entropy gradient or a gradient of the rotational velocity with the appropriate sign.
Why has to do with rotation? It's a local condition.
But you have to have this. I may jump to another talk, but we may chat about that afterwards.
You locally have the Coriolis force acting. That's exactly local, and so you have a linear shear flow. Both are local. And if you don't have the rotation, you don't have MRI. You have the marginally
so how did they do?
non-linear shear flow instability. It's quite a different problem.
The first simulations were just shear box of MRI.
Right, where they have a gradient in. Right. They have a gradient of the some velocity gradient, right?
Okay, so
Meaning
that's
radial velocity
you have
gradient.
a huge
I have a
gradient.
gradient here.
It's a
Yes,
huge
that's what I
gradient.
mean. This is a extreme case of an MRI setting, but this is not what you would typically look for in disks or in stars, because you have a radial gradient with not this kind of jumps. If you have this kind of jumps, you better do this kind of Curie box like that.
And here you have, did you say entropy gradient?
No. Here, we will have that, but in other
density,
models. This
how
is just
about
the basic thing.
That's right.
Zero
How about
entropy, constant density, constant pressure,
Yes.
only sharing.
But there's an inflection point in the profile, right?
Right. This is true.
So then you have an inflection point here for instability.
This is true, but we have also studied what happens when you have a density gradient or entropy gradient and so on and so forth. And the results are as you would expect. Basically here, since we smooth the profile into a small into a small transition layer of small width, you effectively have a shear and a change of properties very soon after you start your simulation. The density starts to follow.
So I guess there's a question before, is the rotation important or not? Like in the case of the merging neutron stars.
Okay, here
the
so
whole
far
thing was kind of spinning around.
Right. So far here, we concentrated on an idealized case. We want to understand, because that's the first time we face this problem. So my idea was to learn, first of all, and then we apply the thing to more sophisticated initial models, trying to mimic neutron star merger interfaces.
Sure, then also just to find, is that this instability for all nodes, doesn't that depend on the velocity of the shear, if it's supersonic, for example?
Okay, this comes later. Okay. So this is a summary, right, of what happens. Previously, this problem has been studied, right, in 2D, for example, for weak fields. You see that if you have relatively strong fields, but not too strong to dump completely the growth of any Kelvin-Helmholtz vortex, for the Albert number slightly larger than 2, then you have nonlinear stabilization. This means that the field is initially too weak to dump the development of the vortex, but in less than a vortex overturn, it grows to values, right, because you amplify the field in this vortex, to values that suppress further winding of the field, and that's the end of the instability. Now, in this case, the field is concentrated in very thin sheets and annihilates in the long term in localized reconnection sites, mediating the conversion of kinetic to internal energy through the buildup of magnetic energies. This destroys the vortex. And the late evolution consists of a broad transition layer where the flow is basically parallel to the initial shear layer. No vortex is retained, and because of reconnection, there is a strong decrease of the magnetic field, which concentrates, as I said, in elongated patterns, elongated sheet-like patterns along the shear layer. If you consider even weaker fields, there are two possibilities. If the field is weak but not too weak, you find disruptive dynamics. What is it? Eventually, you form the Kelvin-Helmholtz vortex, so you amplify the field, right? It can roll on several times, and the vortex therefore retains its coherence for longer cycles. In this process, the field as it's wound up, it's rolled in sheets which are progressively thinner and thinner, which eventually, because of numerical resistivity, reconnect and make the field to saturate, the growth of the field to saturate. The late evolution is similar to this one, so a broad transition layer where the flow is rather laminar than turbulent. Now, if you go to really weak fields, you find what people call dissipative dynamics, right? After a long phase of amplification, many vortex turns, the field in this amplification cannot grow to affect the dynamics of the velocity field. It's not dynamically relevant, but still reconnection occurs, but at a much smaller level, and therefore there is a more gradual conversion of kinetic into internal energy. And in the late times, you see that the vortex is retained and is coherent with decreasing velocity, as secularly the kinetic energy of the vortex is extracted by magnetic stresses. Of course, the transition between these two regimes is not clear in A. I mean, there is no a value of the Alfvén number that separates the two evolutions, right? This is 2D. In 3D, the picture complicates because, well, depending on whether you develop what the so-called elliptic or parasitic secondary hydrodynamic instabilities, which I will explain later if I have time, which add on top of the MHD instabilities and which have been studied by Ryu and co-workers. I don't know how long should I go on with this because since
it's already an hour and 10 minutes since you're starting. So.
Okay.
Lunch is 12:30.
Okay. Fine. So, as I said yesterday, to sketch more clearly the numerical setup in 2D, we want first of all to check that all the previous results in 2D, right, to learn what is going on. We use ideal gas equation of state, a transition layer with a thickness A, initial magnetic field just parallel to the x-axis, and we have a transition in the velocity, which is smoothed with a hyperbolic tangent. And to trigger the instability, we just put some sinusoidal variation with a very small amplitude in the y direction. Otherwise, you have to wait too long for this to happen. But as you see, the initial strength of the y velocity, it's very small compared to the shearing velocity.
What's the wavelength?
We don't stimulate a particular wavelength. Just there is a random function here that picks values between 0 and 1. Now, first of all, we validate the code by comparing by computing the linear growth of the instability for weak, sufficiently weak fields, right? So this is, for example, this corresponds to a purely hydrodynamic model, right? No magnetic field in the subsonic regime, right? And then you see here that the growth rate matches with the analytic expectations very well. So
what are you measuring?
Sorry?
What are you measuring?
Simply the exponential folding of the. This is a kinetic energy in the y direction, right? When you don't have magnetic field, a way to see you convert transverse, so parallel to the shear layer velocity to perpendicular direction when you roll on the vortex. So, and this grows exponentially, right? In a Kelvin-Helmholtz typical instability, and it has to grow at a certain rate, which you can compute with by linear theory. And you see that there's a perfect matching. We have run a number of models to show that, right? And basically, our models reproduce what Heppens and co-workers or Mura and Pritchett in the early 80s obtained, right? Now, let's make it short because this is just to produce previous results. We have tested the influence of the boundary conditions and the domain size on these simulations, right? And then what we have done here is, for example, to test the growth in the supersonic region, which was already studied by Mura and Pritchett, and they argue that for a Mach number m larger or equal than 2, there is no growth of the Kelvin-Helmholtz instability. The flow is too fast to develop any role. And well, what we find is that, for example, let me see, smaller domains, right? This is the size of the domain in the x and y directions. Smaller domains in the y direction, which are the ones which are relevant, because along the x direction we put periodic boundary conditions, right? So this is not influencing the dynamics, but along the y direction you can choose whatever you want there, right? We choose, for example, open or reflecting boundary conditions to see extreme cases. And for example, if you look at this model, right, this is a pure hydro model, supersonic, right, with Mach number 1.8, right? And if you look at the growth rate in the linear regime, and you look at the counterpart with closed boundaries, you see the same growth rate. So in this case, the boundaries are sufficiently far away for the dynamics, at least in the linear regime, not to be affected. Of course, if you make the domain sufficiently small, this doesn't happen anymore, and you see that if you have open boundaries, the growth rate is much reduced with respect to closed boundaries. And that's because in closed boundaries you don't leave, you have reflections of acoustic waves or even that can be steepening to shock waves,
What's the unit of the
affecting the domain.
Units of
The gross.
Right? Sorry?
What's the unit of the gross right here?
What's the unit of what? It's dimensionless. It's 1 over time. I mean, 10 units are whichever. No, here there are no physical units. It's dimensionless. Always dimensionless simulation, right? There is no.
How do I translate?
Later it comes this thing.
But the linear growth rate, does that happen on a time scale that's short compared to the sound crossing time of the box, or is it?
Right. This happens. This is what happens. Yes. But you see here how different it is when you put different box sizes.
But what's
right.
what's the sound crossing time in those units? T.
Let me see. You have here Mach number 2, and you have initially it's about 1 or something like this.
Oh, so it's 40.
So it's many sound crossing times here.
Is A the sound speed?
A is the thickness of the transition layer, right? In units of, Lx is 1, right? So it's about 5% of the total domain. Right. The instability affects, of course, a larger area, if a relative area, if Ly is sufficiently large, right? In the other case, when you have two close boundaries, well, these waves go away and cannot affect the dynamics. And in the supersonic regime, we find that the sound waves created at the shear layer can steepen into shocks, and they can travel away, if they can travel away for a sufficient long distance. And then these sound or shock waves leaving the domain are responsible for this oscillatory growth instead of a linear exponential growth. Only if shock forms in the supersonic regime, a vortex-like structure develops. And the y distance that these shocks can travel, so perpendicular to the shear layer, depends on the Mach number. For example, for the sonic case, m equals 1, shocks are restricted to a relatively small layer around the initial transition layer, and that explains why we don't have basically influence for the boundary conditions when in this case.
Sorry, why don't you try a box that's long enough that its crossing time is longer than you're looking at? Like, so I think people do that. They usually do a very long box so that the.
Well, we multiply by 2 this, and you see the growth rate. It's basically unaffected. Actually, there are many more models. We multiply by 8, and the thing was basically unaffected.
But you could do that, right? In 2D, you have enough.
Yeah. As I said, that we did it, but we have to. There are more than 300 models run for this work, and we had to somehow choose some, right? To basically, this is only to demonstrate that the code works. Because those results, except for the supersonic regime and why this happens, this was not explored previously. Right? Those are new results, right? But basically, we are reproducing things that other people have done. Now, as I said, what we find in contrast with previous work is that even when the Mach number is larger than 2, larger or equal than 2, depending on the boundaries that you put, you can have growth, right? And growth of the instability. So supersonic models with reflective boundary conditions where there is a growth of the instability. But here, the growth of the instability is mediated by shocks, right? And these shocks, they do like this. They start to form in the perpendicular direction to the shear layer, and the fluid tries to slide along, converting the transverse, so paragel kinetic energy, so the kinetic energy associated to the x component of the velocity to y velocity, to kinetic energy in the y direction. Now, after the Kelvin-Helmholtz phase, we have an stabilization for intermediate fields, so for intermediate field strengths, meaning by that field initial configurations where the Abel number goes between 2 and 5, roughly. So, so we find that this nonlinear stabilization works, as I said, in less than 1, or at most 1 Kelvin-Helmholtz vortex turnover, you just stabilize the flow in agreement with Frank and coworkers. Now, few notes on numerical resistivity. When you go to very large Reynolds numbers, the energy should be transferred to ever smaller scales by turbulent cascades. Now, in numerical simulations, this energy eventually reaches the scale set by the grid size. And therefore, it cannot be represented by the discretized magnetic fields. Therefore, what the code does is to assign such energy to the internal energy of the flow. And the physical resistivity also transfers magnetic field energy into internal energy. Thus, one could hope that numerical resistivity acts as a subgrid model for the unresolved dynamics, just as a hope. In models with intermediate fields, due to this numerical resistivity, we see the emergence of coherent flow and field structures, which are subsequently disrupted by the reconnection of the field in thin flat sheets, and therefore this efficient conversion of kinetic to internal energy happens, and this is much more efficient than in the non-magnetized case. As I said, the final flow is rather laminar than turbulent, and our results agree with previously produced by Jones and co-workers. Now, if we go to weaker fields with initial Alpern numbers from 125 to 5,000, compute with numerical resolutions up to 4,096 squared, we identify the same disruption and dissipation regimes already seen by Jones and co-workers. So in the disruption regime, the magnetic field finally it's destroyed by the growth of steering mode instabilities, and these steering mode instabilities behave as a catalyst to convert kinetic to internal energy. In the dissipation regime, the same effects are basically seen, but the growth of magnetic field is not sufficiently strong, and therefore the steering modes are not sufficient to fully disrupt the vortex, or they do it in over a longer time. Finally, we get here a turbulence. Here there is a broad transition layer, and here you have a turbulent layer where the flow and the field decay slowly, right? We have found in our simulations three phases of the Kelvin-Helmholtz instability. The Kelvin-Helmholtz phase, which is just the one predicted by the linear theory, exponential growth of the field. A kinematic phase, where there can be amplification of the magnetic field after deformation of the vortex, which evolves secularly. This cannot be predicted by linear theory. And finally, this dissipation or disruption phase, which, as I will explain, we think only the disruption phase is the physical one, where the Kelvin-Helmholtz vortex loses its magnetic energy because of Maxwell stresses. So, for example, here I show the evolution of the magnetic energy in the y direction and the kinetic energy in the y direction, which are a measure of the turbulent energies, right? Kinetic or magnetic, right? Because those are the ones perpendicular to the interface. So you see the initial phase of exponential growth for both models with Alpern number 5000 and 825. And then here I scale the time according to the end of this linear growth. And then after a while, you see that the kinetic energy in the y direction doesn't grow anymore. It's just levels off. And but still, the magnetic energy, which is this line, for example, here, still grows, right, until it saturates. That sets the end of this kinematic amplification phase. In all this phase, up to here, right, up to the Kelvin-Helmholtz phase, up to this line here at equals 0, the field grows passively without back reaction on the dynamics, and we get a more or less rather constant amplification factor for the magnetic field strength at the end of this phase, which is of the order of 1.4 that we have at the beginning of the simulation. And the magnetic energy in the y direction, it's about 10% of the total magnetic energy in the flow.
So this is 2D.
This is 2D so far. As you can see here, we have run models with increasingly large number of zones, right? Denoted here in different colors. And the numerical growth rate is the same, right? You put here one model on top of each other simply by scaling the model of this large number by 5,000 over 125 just to have the same energy. And then you see that both have the same growth rate initially. Even also the evolution is quite much the same until they start to separate after the end of the amplification phase.
Why is it break?
Sorry? As I said, the kinetic energy in the y direction levels off. Even you have formed the vortex.
That's a break.
Right. But still you wind up the field. Right? So it amplifies.
Yeah.
It does amplification more than linear. Right? During this phase. It's exponential also. Now this is, for example, a determination of the Kelvin-Helmholtz phase. What, right? So here is just the vortex is just well, this is periodic, right? So it catches just this is just continues over here. And this is just for this model with this is a sonic model with a 125. And what you see here is just this is a complicated thing. You see here that the lightness in the model represents the Alpen number, while the color represents the sound speed. So you see that the model becomes, even if it's sonic initially, it becomes supersonic over these thin flux sheets. And it's basically subalbenic everywhere. Subalbenic everywhere, sorry. Now, okay. In the second phase, this kinematic amplification phase, the growth rate for the magnetic field is basically the same, independent of the initial Alpen number of the flow, right? And there is again exponential amplification of the field beyond the linear regime.
But increasing the resolution, you see it that keeps on somehow. Will you say that you have?
I come to that. This is, for example, the structure of the flow before the end of the Kelvin-Helmholtz phase, right? This is just for A5000 and A125. You see that. Just to show you a picture, the up panel is the velocity and the down panel is the Alpen speed, and you can see, as I said, that the flow is subalbenic, except perhaps in some thin flux sheets where the magnetic field has amplified quite a lot, right? But basically, they look much the same. Now, to understand how this kinematic amplification phase works, we can work out which is the evolution equation for the magnetic energy density, and then you see that this is an advection equation with a source term, where you have a term which accounts for the growth of the field in case of compression, and there is another term that accounts for the growth of the field because of winding. Now, since our flow is basically incompressible, what makes the field to grow is this winding term, which basically, when these two guys have integrated over volume positive sign, this just leads to, it's just a constant, right? Because it is like the curve of the velocity field, which is fixed, the flow is uncompressible, times this magnetic energy. So you see here that this equation just yields exponential amplification of the magnetic field. And actually, if you represent this source term, right, what you see is that, well, when the source term is positive, there is a net creation of magnetic energy, and when the source term is black or brown, then it's destruction. So most of the generation of the field occurs not everywhere, but concentrated in thin fluxes, right, which are well resolved, and thus the growth rate is independent of resolution. That explains why the growth rate is independent of resolution. Now, the termination phase, as you can see here, depends, as we were saying, on resolution. What I plot here is what I call the amplification factor, which is the ratio of the Maxwell stresses at the end of the amplification phase to the Maxwell stress at the end of the Kelvin-Helmholtz phase. And then you see that when you go to very poor resolutions, it is true that, well, you know, if you look at the black dots, which corresponds to a so a strong field, until you don't reach a certain resolution, you don't level off. So you haven't found convergence. Of course, to find convergence, you need to, for weaker fields, you need to go to increasingly higher resolutions. But we have found a limiting or a scaling law telling us which is this amplification factor as a function of resolution. So it scales, basically, we have plotted like this, with this gray region, like the resolution, the number of points per dimensions per dimension to the 6, 7, 8. For the Alfvén number is the same. So for weak fields, for strong fields, we get, well, when the points are clustered together, this corresponds to different resolutions, right? You can see it here. So when the field is sufficiently strong, we have convergence. But when the field is not sufficiently strong, you have this scatter in this direction. We have estimated which is the maximum scatter that you can have, and we think that there is a maximum amplification that you can get during this phase independent of resolution. Let's see why. To quantify the resolution effects, we define the typical length scale for variation of the magnetic field as the ratio of the magnetic field strength to the curl of the magnetic field, basically the current without factors. Now, because of flux conservation, the scale of the magnetic field decreases from initially it's infinity because you have just a parallel magnetic field without any curl to a finite volume, and as you wind up the vortex. Now, the minimum value of that can take LV is just the scale of the grid resolution. Now, if this scale reaches this H, then the magnetic field cannot keep growing, and that causes the end of this phase. So, in this plot, you see here in this basically white, where the length is of the order of 1 grid cell. Right. But now we have found that there exists a maximum field that is attainable, which is proportional to the initial field times the thickness of the transition layer over the width of the width of a single zone, which tells which is the maximum field that you can reach. And this can only be reached if the flow initially has a magnetic field sufficiently weak. So Alfvén numbers are smaller than 1,000 to 150, and this is because otherwise you affect the dynamics of the flow because of the growth of the magnetic field. Now, even if A is larger than this value, we find that nowhere the magnetic energy at the end of the amplification phase is larger than the kinetic energy of the flow. So we don't reach equipartition in this case, and the flow is extremely super Alfvén. Now, I don't know how much should I keep, because since I did the tour,
you should converge.
So, this is just to show where the local equipartition is reached when you start to develop this reconnection. And the point here is that reconnection is produced in a dynamical background, right? Typically, one expects from the works of Biscamp that if you have a current sheet in a fixed background, as you increase the resolution, you lower the resistivity, and therefore there's no convergence. But what happens here is that resistive instabilities develop when several flux sheets come close to each other affected by the field. So it's not the thickness of each individual guys what determines the growth of Turing modes. It's just that you put them together because you have a convergence flow. And then when the distance separation between these current sheets goes to the grid size is when you start to have resistive instabilities. Now, this is very different to the static background case, and therefore this distance is not related to the magnetic energy stored by the flux sheets, but is determined by the flow field. So, since we have a very well resolved flow field, right, which is given by the dynamics of the Kelvin-Helmholtz vortex, it does not depend strongly on resolution. Therefore, there is a moment at which the flux sheets break up and the energy is released because of these reconnections, and that's why we have convergence despite of the grid scale effects. Because, as I said, it's just that you affect these current sheets together, and not because you make very thin current sheets that eventually dissipate. So that's the key difference, and that's why we get convergence. So I skip all this thing because it's way too much, just to show some how the field saturates after the end of the, after this amplification phase, we reach saturation, dissipation, and disruption of the field. The vortex is completely disrupted. Here you have the y component of the velocity field. Here you have the magnetic field strength, right? And we find some sort of a steady state in a statistical sense, where there is a kind of turbulent transition layer.
This is because of the net flux of the field.
Well, there is a periodic boundary.
There is net flux, otherwise you don't have to be dynamo.
Right, but okay, yeah, well, okay, yes, you have a periodic, yes. And now, how long does it take to reach this state? And how long does it take to accelerate the vortex? We have worked out this thing, and it turns out that the time it takes to accelerate the vortex is proportional to the initial magnetic field to the minus 0.7. And also the time it takes to disrupt or accelerate the vortex, both are proportional to this initial field, to this power. Now, in 3D, right, as I said, there is what happens is that this is just the entropy of the flow or the curve of the velocity field at two different times by the end of the Kelvin-Helmholtz phase and when the field saturates. And the thing is that here there is a competition. Well, in 3D we find basically the same phases as in 2D, right? But here parasitic elliptic instabilities develop as the vortex grows. So they try to shake a bit the vortex, and this makes that pure hydrodynamics just limits the growth of the field. No further winding of the field happen, right? And then depending on who of the two wins, whether this parasitic hydrodynamic instabilities or just the field amplification to become sufficiently strong to affect the flow, you get one outcome or another, right? If the magnetic field stresses win, then you have basically the same dynamics than in 2D. If the hydro instabilities win, then you have basically isotropically decaying turbulent. And well, okay, I should skip this because it's too long. I think it's too much. I'm sorry, but I didn't expect to go on this tour of mergers of neutron stars. And here it comes just simply to show the setup for particularly for mergers of neutron stars, where we just simulate a small box here, assuming that the shear layer is simply plane parallel, right? There is no curvature effects in these models, but we have a gradient of both the density and the gravitational potential, right? Which we mimic. You know, we assume that there is those are not. Those are the potential that fills this surface layer is just like a quadruple potential, sort of, just to mimic this non-radial effects when you have these two neutron stars. And we do simulations in 2D and in 3D, and basically what we find is that we reproduce what we have found in dimensionless magnetic field, in dimensionless simulations, right? And the key point is that starting with fields of the same order of Price and Rosebach, we find that the Kelvin-Helmholtz vortex develops in less than 0.05 milliseconds with a wavelength similar to the grid size along the x direction. And for fields of the order of 5 times 10 to the 13 or 10 to the 14 Gauss, we may eventually reach, in very local regions, field strengths of the order of 3 times 10 to the 15 Gauss. But if you look at the root mean square fields average over time and space, right, in these simulations, when you reach saturation, the average field is much smaller, by more than one order of magnitude smaller.
But that's the field, but the energy is larger because it's b squared.
No, because it's localized in very small, it's localized in very small volumes.
I understand, but the field is weaker than, the energy goes like b squared, right?
Right.
So I think if you average over energy.
Right, if you decrease the average, if you look at the average volume energy, it's also smaller by a factor of 100. Because it happens in very small regions. It's not everywhere in the volume that you reach these high magnetic fields. The acceleration times are of the order of 1 millisecond for this magnetic field strength, and you reach the turbulent outcome in less than 0.5 seconds, right? Now, just to finish, I mean, in 3D, we get similar results, right? And just to sum up, we have performed more than 300 numerical models to assess the impact of the growth of Kelvin Helmholtz instabilities in contact layers of neutron stars. The magnetic field never reaches equipartition with the internal energy, neither the maximum nor the root mean square. Therefore, this huge magnetic field strength,
this is anyhow impossible because it's above the buoyancy limit. You know,
right.
It's going to be buoyant anyhow. So.
Right, but you know, I mean, our fields are sufficiently well below this limit to rule it out. Locally, we can have equipartition between the magnetic energy and the kinetic energy, implying magnetic field strengths as large as 10 to the 16 Gauss in 3D, right, as speculated by Price and Rothko, but only locally. The root mean square is never larger than a few times 10 to the 15 Gauss at most, and therefore its direct dynamical impact on the acceleration of the shear flow, the disruption of the vortex, or whatever is rather limited. And both the maximum and the root mean square are even smaller in the geometry of the system, and or the dynamics yield to a large role of the hydrodynamic stability. If you have a flow which is just perturb a bit, you shake a bit the flow in the direction perpendicular to the equatorial plane, then these parasitic 3D stabilities terminate the growth much earlier, and it can be 1 order of magnitude even smaller. And just to finish,
what's the scale in which this magnetic field persists?
What?
The scale in which this magnetic field can persist, like 10 to the 15 or 10 to the 16?
This is only for 1.5 to 2 milliseconds at most.
Okay.
The maximum values. So the small time scales actually over which this Vmax is obtained impose severe constraints on the impact that these amplified fields may have on the hydrodynamic or electromagnetic jet launching mechanism. So as Komisarov has told us, and also Maxim Barkov told us, the magnetic-driven relativistic outflows need much more longer times of a few milliseconds to tap the rotational energy of the black hole or of the accretion disk to produce the outflow. Though these results might limit the prospect for the effects of magnetic fields in mergers, one should take them into account because locally the dynamics can be rather different, and this can affect, for example, how long may the disk that forms it from the neutron star merger persist, which is relevant for setting the scale of short gamma reversed, and that's it for me.
Almost you broke a record.
I had 100 questions before. We have more questions. One more question on the back there.
What typical temperatures would you expect in this?
What typical temperatures?
Yeah, this shear lane layer.
In these models, what we have is an idealized equation of the state, where one part there is at 0 temperature, right, for the nuclear matter density, and the thermal part gives us